This is Applied Calculus, Section 3.2, Derivatives of Exponential and Logarithmic Equations. We're going to begin with the proof of the derivative for e to the x. Given that f of x is e to the x, find f prime of x, its derivative. We begin by recalling the derivative formula using the limits, and that's because e to the x is a derivative we've never encountered before, so we need to go through the limit definition and determine if there's a pattern we can use for e to the x derivatives. So we begin by replacing the x with x plus h, and that gives us e to the x plus h power, and f of x plus h minus f of x would give us e to the x plus h minus e to the x, and that's what we see down here in the numerator, and the denominator is simply h, and the limit as h goes to 0. Now we can factor out an e to the x here, and we can rewrite e to the x plus h using properties of exponents. Recall, if I had x squared times x to the third, that would be x to the fifth. So x to the 2 plus 3 could be split up into x squared times x to the third, while e to the x plus h could be split up to e to the x times e to the h. Because the bases match, we add the exponents. So we've split up e to the x plus h into e to the x times e to the h, and now we can factor e to the x out of both the first and second term, and that's how we get this numerator rewritten as you see here. So now we can incorporate some limit properties. The limit of a product is equal to the product of the limits. So we can take the product inside the limit and split it into two limits. Well, here's our product. We have e to the x times e to the h minus 1 over h. So we split it up into the product of two limits. The first limit we want to evaluate here is the limit of e to the x as h goes to 0. Notice that since there is no h variable, we treat like a constant. So the limit as x goes to a for a constant c is equal to c. Doesn't matter what x goes to. The limit as h goes to 0 for e to the x is e to the x because there is no h variable. So now we have to evaluate the other limit. The limit as h goes to 0 of e to the h minus 1 all over h. Well, this would give us e to the 0 minus 1 over 0, which would be 1 minus 1 over 0, which would be 0 over 0, and this is indeterminate form. So we can't use direct substitution. Direct substitution fails. And now you have to choose a numerical process. So you can create a table of values, or you can graph it. I'm going to use the graphing method here. You can create a table of values. You'll get the same result. So we see that we have e to the h minus 1 over h, and right now h is at 2, and that puts us at this point you see here, just above 3. And if I take the slider and move it, we see that as we move towards 0, we are approaching 1. When we get to 0, the point disappears because there is a hole there. I can go from the left side. I'm at -2 and approach it. Moving from the left, I'm getting closer and closer to 0. Once I get to 0, it disappears because there's a hole there. So we would say I'm squeezing the same value on both sides, and that the limit as h goes to 0 is 1. So now that we know the limit is 1, we can replace this with 1, and this stays as e to the x. So we're left with e to the x times 1, and that means the derivative of e to the x is itself. So now we can apply this to some examples you see. If f of x is 5e to the x minus 3x to the fourth plus 9x plus 16, what is f prime of x? Well, remember, we can take this on a case-by-case basis. I can factor out the constant. And I can evaluate each derivative term by term. I can factor out constants out in front if it helps me to understand each derivative. And the derivative of e to the x is itself, and the 5 will multiply that. Next, the derivative of 3x to the fourth is 12x third. Then the derivative of 9x is 9, and the derivative of 16 is 0. So f prime of x is equal to 5e to the x minus 12x cubed plus 9. So let's look at b. This first term is meant to trick us. That is not e to the x, it is x to the e. Remember that e is a constant. So f prime of x is going to be negative 7 times e to the x to the e minus 1 power plus, now I have an e to the x term. 2e to the x will be 2e to the x. We can take the constant out and just focus on e to the x, which is its own derivative, and then multiply the constant back in once we're done, and we get 2e to the x. And once again, we have to remember e is a constant, so a constant squared is a constant. And what is the derivative of a constant? It is 0. So this is our f prime of x for b. Next, we want to look at derivative of natural log of x. So we want to recall some of the properties first. We have here our limit of a composition of functions. So the limit of f of g of x is the same as f evaluated at the limit of g of x. And then we will be using our limit definition formula again because we've never seen the derivative of natural log of x before. So since it's the first time, we use the derivative definition with the limits. We are going to recall our limit definition of e. So step 1, substitute natural log of x into the limit definition of the derivative. So to find the derivative of ln of x, we're going to take ln of x plus h minus ln of x in the numerator all over h. And now we can use log properties to rewrite the numerator. So this is the difference of logs property. Ln of a minus ln of b is equal to ln of a over b. So this is our a, this is our b, and you'll notice that we have x plus h over x in the second representation of our limit. Now we're going to use some algebra. We can say that x plus h divided by x is equal to x over x plus h over x. The x over x simplifies to a 1, and the h over x does not simplify. And that's what is in the numerator now. We are going to factor out the 1 over h from the natural log. So natural log of 1 plus h over x over h could be written as 1 over h times natural log of 1 plus h over x. These are the same. Just factored it out. When we factor it out, we can use a log property to move that into the exponent, which is what we see here now. 1 over h is in the exponent. So our next step is to move the limit from in front of the log to the inside of the log. This was our limit property that said the limit of f of g of x is equal to f of the limit of g of x. So that's the composition property. And now that we have the limit moved to the inside of the log, we can take the limit of this expression. And We should recognize the format of this expression, but to help us even more, we're going to say rewrite h over x as 1 over x over 1 over h. 1 over x over 1 over h is equal to 1 over x divided by 1 over h. And when you divide by a fraction, that's the same as multiplying by its reciprocal. So just to show you that 1 over x over 1 over h is the same as h over x. In doing that, we're getting closer and closer to rewriting this to look like our number e. So now we're going to say let n be equal to 1 over h. And now I can replace 1 over h with n. And we see that as 0 goes to h, n goes to infinity. And this gives us our definition of e to the x. Only the x is 1 over x, so it's e to the 1 over x power. And we can say that the log of e of 1 over x can take the power property for logs and write it as 1 over x times ln of e. And we know that ln of e is equal to 1. So the derivative of natural log of x is 1 over x. Now we can use this in some practice problems. In part A, if we're looking for y prime, that means we're looking for the derivative of each term. And we can move the constants out in front. So 3 times d dx of e to the x plus 5 times d dx of ln of x. And we did the derivative of e to the x in the first half. So that's 3e to the x plus 5. And the derivative of ln of x is 1 over x. So y prime is 3e to the x plus 5 over x. So try part B on your own. Pause the video, see what you get, then unpause to see if your result matches. So first I'm going to rewrite y equals x to the fourth minus 4 times ln of x. I used the power property for logs. Y prime is the derivative of each term. And this is what you should get. So we have our derivative of e to the x is defined, but now we have if the base is different from e. So for example, if I had d dx of 5 to the x power, it would be 5 to the x times ln of 5. The same is true for natural log of x. This is understood to have a base of e. And now we're saying let's change our base to some other number. So if we had d dx of log base 3 of x, it would be 1 over the natural log of 3 times 1 over x. Times 1 over x, which is 1 over ln of 3 times x. So for part A, g prime of x, we're going to use the exponential base formula. So that's going to be 2 to the x ln of 2 minus 3 to the x ln of 3. We did it on a term-by-term basis, and this is our answer. For example B, g prime of x, because the base is not base e, it's base 4, we're going to write 1 over natural log of 4 times 1 over x, or 1 over ln of 4 times x. Remember that this is a constant. An internet store sells Australian wool blankets. If the store sells X blankets at a price of P dollars per blanket, then the price demand equation would be P equals 350 times 0.999 to the x power. Find the rate of change of the price with respect to demand when the demand of 800 blankets is Find the rate of change of price with respect to demand when the demand is 800 blankets and interpret the results. So P prime equals rate of change in price P prime is equal to 350 times d dx of 0.999 raised to the x. This is an exponential function that is not base e. So P prime is 350 times 0.999 to the x times ln of 0.999. So we can enter this in our calculator. We're going to substitute 800 in for x. So P prime of 800 gives us negative 0.157. So what this means is that when demand is at x equals 800, the price is dropping by 16 cents per blanket. So here's an application for franchise locations, and they give us this model for growth of number of sandwich shops. And if T is the number of locations they have, when T equals 0, that represents the year 1980. Use this model to estimate the number of locations in 2028 and the rate of change of the number of locations in 2028. Round both to the nearest integer, interpret these results. So 2028 means we're talking about T equal to 48. So that's 48 years after the year 1980. We can evaluate n of 48 to find the number of locations in the year 2028. And that would be negative 765 plus 482 times natural log of 48. You plug this into your calculator and get 1,101 locations approximately. And next you'll calculate the derivative of n of t. So the derivative of 765, that's a constant, that would become 0. And the derivative of 482 ln of t would be equal to 482 times 1 over t. So n prime of 48 would give us 482 over 48, which is about 10. And this means that the number of locations is increasing by about 10 per year. And that's occurring in 2028. So this is the end of the lecture. You can go back and watch it again, complete the practice problems, and come to class with questions.